Logistic regression. Introduction. Logistic regression is done when the outcome variable is a dichotomous categorical variable, such as a disease, present or absent, vaccinated, yes or no, and an outcome, died or did not die. The purposes of logistic regression analysis and other multivariable analysis are to a. Adjust the estimate of risk, odds ratio, for a number of confounding factors set in the model. b. Determine the relative contribution of factors to a single outcome. c. Predict the probability of an outcome for a number of independent variables in the model. And d. Assess interaction of multiple variables for the outcome. Data file. Scenario. We conducted an unmatched case control study to identify the factors, or predictors, associated with diabetes, dependent variable. The independent variables, CB's factors, that you have considered for analysis are sex, variable name, sex1, age, peptic ulcer, variable name, peptic ulcer, and family history of diabetes, variable name, AE4 history. To perform the unconditional logistic regression analysis, recode diabetes as 0 equals diabetes absent and 1 equals diabetes present, if it is not coded like this. Similarly, it is better to recode the categorical independent predictor variables as 0 for no, comparison group, and 1 for yes. Commands: analyze next regression, next binary logistic. Next, put diabetes in the dependent box. Next, put age, sex1, F history, and peptic ulcer in the covariates box next. Categorical next. Push sex1, F history, and peptic ulcer from covariates box to categorical covariates box next. Select sex1, next select first for reference category under change contrast. We are doing this because 0, female, is our comparison group. Note that the default category for comparison is the last category. Next, click on Change. Next, do the same thing for all the variables in categorical covariates box. Next, Continue, Next Options, Next Select. Classification plots. Hosmer-Lemshow goodness of fit. Case-wise listing of residuals, correlations of estimates, and CI for XPB. Next, Continue, Next, OK. Commands. Outputs and interpretation. Table 14.1, Case Processing Summary, shows that the analysis includes all the 210 subjects. Value. If there are any missing data, this table will show it. Note that the subjects are excluded from analysis if there are any missing data. Table 14.2, Dependent Variable Encoding, tells us which category of the dependent variable, diabetes, is the predicted outcome. The higher value is the predicted outcome. Here, the higher value is 1, have diabetes, and is the predicted outcome for the dependent variable. Table 14.3, Categorical Variables Codings, indicates the comparison groups of the independent, explanatory, variables. Here, the lower value is the comparison group. For example, for family history of diabetes, no is coded as 0.000, while yes is coded as 1.1000. This means that persons who do not have the family history of diabetes is the comparison group, reference category. Similarly, not having peptic ulcer, 0.000, and being female, 0.000, is the comparison group for peptic ulcer and sex, respectively. Outputs and interpretation. Analysis of data without any independent variable in the model is provided under Block 0. The results indicate the baseline information that can be compared with the results when independent variables are included in the model. The table indicates the overall percentage of correctly classified cases, 78.6%. We will see whether this value has increased with the introduction of independent variables in the model under Block 1. If the value remains the same, it means that the independent variables in the model do not have any influence, Schabarter contribution, to predict diabetes, dependent variable. In our example, the overall percentage has increased to 90.5% after inclusion of the independent variables in the model under Block 1 compared to the value under Block 0, 78.6%. This means that adding independent variables improved the ability of the model to predict the dependent variable. Outputs. Interpretation: omnibus tests of model coefficients. This table indicates whether the overall performance of the model is improved if independent variables are included in the model compared to the model without any independent variables, given under Block 0. We want this test to be significant, p-value less than 0.05. In this example, the p-value of the omnibus test is 0.000, which indicates that the proposed model is better than the model without any predictor, independent variables. Model Summary Table. This table indicates usefulness of the model. The Cox and Snell R-square and Nagelkerke R-square, called pseudo R-square, values provide indication about the amount of variation in the outcome variable that can be explained by the independent variables in the model. In this example, the values of the pseudo R-square are 0.384, Cox and Snell R-square, and 0.593, Nagelkerke R-square, respectively. This means that between 38.4% and 59.3% variation in the outcome variable can be explained by the independent variables set in the model. This information is not needed if the objective of the analysis is to adjust for the odds ratio. Interpretation: Hosmer-Lemshow goodness of fit test. When the intention of analysis is prediction, i.e., to identify the predictors to predict the outcome, then the question is, how good is the model for prediction? This is judged based on the Hosmer-Lemshow goodness of fit test and positive and negative predictive values given in the classification table. The Hosmer-Lemshow test indicates how well the observed and predicted values fit with each other, i.e., observed and predicted probabilities match with each other. The null hypothesis is the model fits, and the p-value is expected to be greater than 0.05, non-significant. If the p-value is not significant, it means that the model is a good fit for prediction, i.e., the observed and predicted values are close together. In this example, the p-value is 0.066, indicating that the model is useful for prediction of the outcome variable. If the test is significant, p less than 0.05, then the model is not good to predict the outcome variable by the independent variables in the model. Note that this information is not needed if the objective of doing logistic regression is to adjust for the confounding factors. Interpretation: classification table. This table indicates how well the model is able to predict the correct category of the dependent variable. Have or do not have the disease. This table shows that the overall accuracy of this model to predict diabetes, with a predicted probability of 0.5 or greater, is 90.5%. This table also shows the sensitivity and specificity of the model as 68.9%, 31 divided by 14 plus 31, and 96.4%, 159 divided by 185, 159 plus 6, respectively. Variables in the equation. This is the most important table to look at. This table shows the results of logistic regression analysis. This table indicates how much each of the independent variables contributes to predict-explain the outcome variable. This table also indicates the adjusted odds ratio, OR, and its 95% confidence interval, CI. The B values, column 3, indicate the logistic regression coefficients of the variables in the model. These values are used to calculate the probability of an individual to have the outcome. The positive values indicate the likelihood for the outcome, while the negative values indicate the less likelihood for the outcome. The exponential of BXPB is the adjusted OR for the categorical variables in the model. Let us see how to interpret the results. There are 4 independent, explanatory variables in the model: age, as a continuous variable, sex, family history of diabetes, and peptic ulcer. The table shows the adjusted OR, XPB, 95% CI for the adjusted OR, and p-value, sig. The adjusted OR for sex is 4.891, 95%, CI, 1.737 to 13.774, which is statistically significant. P equals 0.003. Here, our comparison group is female. See Table 14.3. This indicates that males are 4.9 times more likely to have diabetes compared to females after adjusting or controlling for age, family history of diabetes, and peptic ulcer. Similarly, persons who have the family history of diabetes are 3.1 times more likely. OR 3.06, 95% confidence interval, 1.11 to 8.43, P equals 0.03, to have diabetes compared to those who do not have the family history after adjusting for age, sex, and peptic ulcer. Interpretation. Checking for multicollinearity. It is important to check for multicollinearity of the independent variables in the model. If there is multicollinearity, the model becomes dubious. Multicollinearity is checked in the correlation matrix table. This table shows the correlations, correlation coefficients, or R values, between the independent variables. If there is multicollinearity, R values would be high, greater than 0.5. If we look at the correlation matrix table, none of the values are greater than 0.5 except for the correlation between age and constant, which is negative 0.932. If multicollinearity is present and affects the model, the magnitude of the SE's, standard errors, would be high or low, greater than 5.0 or less than 0.001. Existence of multicollinearity means that the model is not statistically stable. To solve the problem, in general, look at the SE and omit the variable as with large or small SE until the magnitude of the SES hover between 0.001 and 5.0. Interpretation. Case-wise list. Table 14.11 provides information about the cases for which the model does not fit well. Look at the Z-resid values, last column of the table. The values above 2.5 are the outliers and do not fit well in the model. The case numbers are shown in column 1. If present, cases that do not fit the model well, all these cases need to be examined closely. Under the predicted group column, you may see Y means yes or N means no. If it is Y, the model predicts that the case number 137 in our example, should have diabetes, but in reality, in the data, the subject does not have diabetes. See the observed column where it is N. Similarly, if it is N under the predicted group, the model predicts that the case should not have diabetes, but in the data, the subject has diabetes. Thank you.